If you have not yet completed this activity, which can also be found above this video, please pause the video and do so now. Now that you've completed this activity, let's see what you would have found. First of all, you will have found that the dimension of the row space of A is 3, the dimension of the column space of A is 3, and the rank of A is also 3. You would have also found that the dimension of the row space of B is 2, the dimension of the column space of B is 2, and the rank of B is 2. From this, you should be seeing a pattern, and the pattern is that all three of those numbers are the same for each matrix. And that is our next theorem. The rank of A, the dimension of the row space of A, and the dimension of the column space of A are the same no matter what matrix we choose. Now let's go to part 2 of the activity. You'll have seen that, well, we already know that the rank of A is 3, and then you will have found that the dimension of the null space of A in this case was 2, and so that sum is equal to 5, which is also the number of columns of A. Similarly, the rank of B is 2, and the dimension of the null space of B is 3. When we add those together, we get 5, which is again the number of columns of B. This brings us to probably one of the two most important theorems in all of linear algebra, and that is the Rank-Nullity Theorem. The Rank-Nullity Theorem says that if A is n by n, then the rank of A plus the nullity of A, which I'll define in a moment, is n. Now the nullity of A, so this guy here, this is just another name for the dimension of the null space of A. Why do I say that this theorem is so important? Well, it's because it makes it so that when we're computing these numbers, we only need to compute one of them, and then we immediately get the other. For example, let's look at this matrix here. The rows of this matrix are linearly independent, and so they form a basis for the row space of M. So we get that the rank of M, which is, remember, the dimension of the row space by theorem 3.24, is 2. But then therefore, the nullity, the dimension of the null space of M, which is the dimension of the solution space of M, is equal to 5 minus the rank of M, which is 5 minus 2, which is 3. On the other hand, what happens when we look at M transpose? We already know that the rank of M transpose is the rank of M, which is still 2. However, M transpose has 2 columns and not 5. So therefore, the nullity of M transpose is 2 minus 2, which is 0. So whereas the rank of a matrix and its transpose are the same, that is not true for the nullity.